All right, so welcome back for part 3 of section 6.1. We're going to pick up where we left off, where we had just calculated the probability, or the percent, if you will, of men and women that would not be, we turn that off, they would not meet the requirements. And we found that for men, that about 0.94% would not meet those height requirements. All right, and let's take a look at women then. Okay, so women are normally distributed, heights are normally distributed with a mean of 63.7, a standard deviation of 2.9. The same requirements are placed on them, that is, it has to be between 62 and 78. So we're still trying to find that piece in the middle. I'm going to do this one the same way I did the last one. I'll find the middle, and then I'll subtract to find the two tails, because what we really want is those people and those people, the ones that are too short and ones that are too tall. So I'm going to grab my calculator, go back to my distribution menu, normal CDF, lower and upper are the same. My mean and my distribution are going to change this time. My mean is now 63.7 with a standard deviation of 2.9. I'll paste that back in, and I get a 72.11. So the middle is 0.7211. And now I'll take 1 minus 0.7211, and I'll get 2789. So now I need to interpret this, and I would say that about 27.89% would not meet the height requirements. Okay. Now, if you're wondering why we couldn't do these two together, like lump them all together, it's because the two populations are different. They have different means and different standard deviations, so we had to treat them as two different populations. All right, so here we have our first example of a normal distribution problem, where it's not just a generic standard normal that means nothing. It's, hey, here's some information that has meaning. It has units of measure. It has an outcome that affects people. Like if I want to be a fighter pilot, I got to know that I need to fit in this range of values to make it. And it looks like basically almost all the men would make it, but almost a third, more than a quarter of the women wouldn't. So yeah, I think maybe they need to redesign the pilot seat or something to make it fit better if they want more women pilots. Okay. All right, so let's add on to this problem and say, hey, if the Navy were to update their height requirements to only include the shortest and tallest 3% of both men and women, what would be those new height requirements? So this is a different problem. This is actually a really challenging problem, because now what they're saying is, what if we wanted to set this up so we only excluded the shortest and tallest 3%? So what if we wanted to find a number for here and a number for here, so that that was 3% and that was 3%, meaning that we would accept all those in the middle between these two values, and we would reject those that we consider too short, and we would reject those that we consider too tall. How am I going to do that? Because that's a much more complicated problem. Well, if I had to do this the old way, I'd have to try to find some value in my table that gave me 3% tails. But luckily, the good people at Texas Instruments expected that you would want to do this problem. And so what we're going to have to do is we're going to have to use the calculator again, but in a slightly different way. Now, they want this for both men and women. This time I'm going to do women first. The mean for women was 63.7 with a standard deviation of 2.9, and these are both inches. So what I want is I want some number of inches right there that's going to cut off that bottom 3%. I'm going to call that my x sub 1, and I want some number over here, an x sub 2, that's going to chop off that top 3%, right? The way that I'm going to solve for x sub 1 is I'm going to use the inverse normal command. And what the inverse normal command does is it takes what we've been doing and turns it backwards. What I mean by that is we've been putting in x's or z's and it's been giving us area. It's going to allow us to put in area and get out x's or z's, right? So I'm going to go back to that same distribution menu, but I'm going to grab that inverse normal command. And now it's going to ask me for the area. And so since I'm solving for x sub 1, I'm going to give it that cumulative area that I want to get rid of. And that's that 0.03 for that 3%. For a mean of 63.7 and a standard deviation of 2.9. And when I paste that in, what I find is that lower value needs to be about 58 point, I'm going to call that 2 inches. And then I'll chop off that lower 3%. Okay. Now, how do I solve for x sub 2? Well, essentially the same way. The problem is, the challenge is that whoever programmed this only ever programmed it to find left tail values. So to find this, we've got to do a left tail where that's going to be 97%. And do you see why it's got to be 97%? So I'll rerun that same command, but this time it's 0.97. And I get a 69.2, roughly, inches. So then, to answer the question, for women, the requirements would be 58.2 inches to 69.2 inches in height. Now, what would change if we went back and did it for men? Well, nothing about the logic of the problem would change, just those two numbers right there. Okay. All right, so the generalized rule here is that we're calculating probabilities. We're finding area and we're correlating that to probability. And we want to use technology. I'm using the TI-8384 graphing calculator. There are other ways to do this. I can't possibly show you every single way. Okay. This is not about memorizing a rule or a formula. We want to focus on understanding. Okay. Draw the graph. Sketch that thing out. Right? Shade the region. Make sure you're looking at a left tail or a right tail, and then use the tech to find the area. Okay. The real work will be in the reading of the problem, setting up the problem, and working it backwards. Okay. The notations we've got here are going to be less thans, greater thans, or in betweens. Now you may notice that all of those are strict inequalities. That first one could be rewritten as this, and it would change nothing. Including or not including that A and that B by making it a less than or less than or equal to doesn't change anything about the area calculation. It's just the way the calculus works. Okay? So we don't focus on whether it's a strict less than or a less than or equal to. That's not a big thing to focus on. Focus on left tails, right tails, and working backwards from there. Finding the proper region using the graphing calculator. Okay. Now we've already looked at this problem, but this is that inverse normal command, right? Where we're told an area and we want to find a a z-score for this one because we're told it's a z. Okay. Remember that the TI can only find left tails. Okay. If you happen to be using a Casio or something like that, it might be able to find right tails as well. I'm not certain. The technology changes literally every year, and I just don't know all of the different calculators. So if you happen to have one that can find right tails, that's great, use it. I'm writing this from the perspective, or delivering this lecture from the perspective of only finding left tails. Okay? It's just using that left tail command. Okay? Also, some more language, notation, information. You might see this phrase critical value. When I say might, you will absolutely see this phrase called critical value showing up. A critical value is just a z-score that separates significantly high or significantly low from everything else. Right? We often use this z sub alpha to represent a z-score with the area of alpha to its right. Right? So when we talk about z sub alphas, we're just saying that, hey, this is a z-score where that alpha means the area to the right. So if I wrote z sub 0.05, that would mean that there's going to be a normal distribution. There's going to be some z-score over here where the area to the right is about 5%. Right? That's all that it's saying. Right? It's just the notation we're using. If we're finding z-scores, if we're finding critical values, all we're doing is this problem again, but we're finding it for a specific area on a tail. Right? Now, this is going to come up because they're going to ask us to find critical values, because this significantly low and significantly high, you may have noticed, is a common reoccurring thing. Like they could go back to that height problem and say, what is a significantly short or a significantly tall man or woman based on that data? Right? How tall would someone have to be considered significantly tall? How short would someone have to be considered significantly short? Okay. The way we find those is we find those using that inverse command. Right? Common critical values are 1%, 5%, and 10%. We just do those a lot. Okay. All right. That kind of brings us to the end of section 6.1. I'm going to stop the video here. We'll come back and we'll start section 6.2. Okay. Have a great day.